Okay, we're back for our last one of the year. We'll be talking about the relationship between energy and mass. We'll be talking about the very last equation that we have not talked about yet on the reference table. Okay, and it is probably the most famous equation in all of physics. You can see it up above my head right now. According to the reference tables, okay, the mass of a proton and the mass of a neutron are approximately the same. You see them all the way down here. Proton, neutron, mass. You don't have to worry about that rest thing. Okay? Right here, 1.67 times 10 to the negative 27th kilograms. Both of the proton and the neutron, I said electron before, I apologize, both of them have a mass that is tiny. But the mass of the electron is even smaller. It's down there on the reference tables as well. 9.11 times 10 to the negative 31st kilograms. There's something with numbers that are this small that make them kind of impractical to use. It takes a lot of effort and energy to keep writing the scientific notation, 10 to the negative 31st, whatever. Scientists devised a different unit, a very small unit of mass. And that very small unit of mass is known as the universal mass unit. And we use the universal mass unit to describe the mass of something inside the proton. You never put a person in universal mass units, okay? One universal mass unit is equal to, and this is not on your reference tables, okay? I am going to show you what it's equal to in an attempt to there is something on the reference tables about this, but it's not. I'm not going to start with it. I'm going to show you where that number comes from. One universal mass unit is equal to 1.66 times 10 to the negative 27th kilograms. Okay, so let's see. The size of the universal mass unit is actually exactly 1/12 of the mass of an atom of carbon. Why they use carbon? Why they use a 12th? I couldn't tell you why they specifically chose those numbers. But basically what happens is this comes out to just about the mass of a proton, just about the mass of a neutron. In universal mass units, if you were to convert, the proton mass would be 1.0073 U. Neutron mass is very slightly heavier, 1.0087 U. They're not exactly the same, it turns out. And the electron mass is really, really small, 0.0005 U. So the electron is still tiny. And now that we're dealing with a unit that is very small, okay, universal mass unit, it makes it a little bit easier to understand what's happening on a nuclear level. And we can actually use this to find out something really weird about mass and energy. I want you to consider an alpha particle. We know that an alpha particle is really just a helium nucleus. And if it's a helium nucleus, that means that it is composed of 2 neutrons and 2 protons. So, we should be able to think about it this way. We have a helium nucleus. If we want to find the mass of the helium nucleus in universal mass units, take twice the neutron mass, because there's 2 neutrons, take twice the proton mass, 2 protons, add those together, and we should get the mass of the helium nucleus. Okay? This is what people did when they were predicting what the mass of the helium nucleus should be. They knew the mass of a proton, they knew the mass of a neutron. They wanted to see what the mass of a helium nucleus would be. So, you do 2 times 1.0073 U for the proton, plus 2 times 1.0087 U for the neutron. You add those together, and you get 4.032 universal mass units. You can check the math yourself. Nothing surprising about that. The surprising part comes now. Turns out that when you have an actual helium atom, the mass of the actual helium atom is 4.0015 U. This isn't an error. It's not a mistake someone made. It's not like someone forgot to zero out the scale. The mass of the helium nucleus, the mass of the helium atom, it really should be nucleus. The mass of the helium nucleus is only 4.0015 U. The mass somehow went down. There is what is a difference that we call a mass defect of, let's see here. I'm not going to do the actual, long subtraction version, but you get an actual difference of 0.0305. 0.0305 U. You take these, they're separate. You add the masses, you get 4.032 U. When you combine them into a helium nucleus, they're smaller, 4.0015 U. The total mass is not the same. This would be like, I can't even think of a good, this would be like taking all my masses, and they're all separate. Let's say you have like 5 1-kilogram masses. Each of them separately is 5 kilograms. When you tie them together with a rubber band or a really light piece of string, it would be like now they're only 4 kilograms. It doesn't make sense. Something weird is going on. Okay? Now, we don't particularly care about exactly how this mass goes missing. We care about what happens to it. It turns out that the missing mass was actually converted directly into energy. This missing mass is used as what we call binding energy. And like I said, I don't need to go into the process. It's the concept of mass turning into energy that is important, okay? Basically, when we're making a nucleus, a helium nucleus, when they're separate, you don't need to bind those protons and neutrons to anything. But when you've got a helium nucleus, we need to bind that together somehow. And we need some binding energy in order to do this. The most important idea is that mass can be converted into energy and vice versa. Modern physics has determined that mass and energy are really just two different types of the same thing. Matter of fact, we don't even call them mass and energy separately anymore. In modern physics, we talk about them together. We refer to this property of something having a certain amount of mass energy with a hyphen in between. On the modern physics level, you need to understand that mass and energy are just two different ways of looking at something. Something that has mass, you can take that mass and convert it right into energy. You can take something with energy and that can become mass. It's very strange, okay? But that is what experiment shows us. As a matter of fact, when this idea came about because of probably the most famous scientist to you guys and in pop culture, Albert Einstein. One of the reasons he's famous is because in his theory of special relativity, he derived an equation for calculating how much energy is stored in a certain amount of mass. In other words, an object with this much mass, if converted to energy, would be this much energy. The equation, very famously, is E equals mc squared. There's a couple of notes that I want to make. For this equation, the mass must be in kilograms. The energy must be in joules. And the c squared part, c stands for the speed of light in a vacuum. Please don't forget that it's squared. Okay, I see people do this all the time. Please remember that the speed of light is squared. When we come back, we will practice using this calculation and using the conversion between universal mass units and something else.